Okay, so we're going to be starting kind of a whole new subject here. We're going to be looking at chapter 10, which is gears, and looking at the kinematic analysis and selection of. So when we kind of bring ourselves back to the kinematics of, remember that's always going to be looking at and only focusing on what are the spatial requirements that we need for the motion that we're looking for without worrying about any forces. Okay, so we are not analyzing forces here. We're not trying to figure out how much torque is going through or anything like that. We're worried about kind of RPMs, velocity ratios we're going to learn about, and really that motion or that speed of the gears as they are meshed together. Okay, so our objectives here in this chapter are going to be looking at different types of gears, really just kind of identifying them in the beginning here, but we are going to focus our attention on spur gears, and those same relationships in spur gears are going to be found in the different types of gears, but they're just going to have a little bit different equations associated with them. So we kind of get our mileage out of spur gears here. So we're going to be looking at determining what that kind of space requirements are through center distances, but then also looking at the velocity ratios and train values. Okay, those are going to be really our outputs, if you would, that we get. And then we would take what we determine kinematics wise with gears, and we would then take it to the next level in, for instance, machine elements class, where now we're going to be looking at what are the forces that are going to be, transmitted, and then what are the materials that are going to be required, and what are the hardness levels. But we're not there yet. We're just in the kinematics part in kinematics class. So we'll be revisiting gears again, which is good. So, so kind of looking at the first part of the chapter here, and specifically section 10.1, the function of a gear is to transmit motion from one rotating shaft to another. Many times we're either going to be increasing or decreasing the speed. Most often it's going to be decreasing. Okay, that's the classic, if you would, application for, if you may even hear something said where we're gearing something down. Okay, we're slowing it down. At times we want to change direction of the rotation, and then also increasing or decreasing torque. Now in kinematics, we're not going to be worrying about torque. We're just going to be worrying about speeds, direction, and then also kind of how much space do we need to get our design, where we need it to be. Many times gears are going to be mounted to, for instance, an electric motor drive, where the electric motor is rotating at a high speed, 1700 RPMs, 1100 RPMs, 900 RPMs, but we need to slow that down so it's usable for an application. So if we look on page 260, which happens to be the first page of the chapter, I'm going to zoom in on the illustration down here, which is figure 10.1. Okay, coming in here, you're going to notice that we have an electric motor that has a gear mounted on the output shaft of it. It's an engagement with another gear. Notice the difference in sizes here. Okay, as we look at the difference in sizes, we're going to be, kind of noting this as we do our calculations and such. But what ends up happening is this gear, because it's mounted on the shaft coming out of the electric motor, is going to be going at the same rotational speed as that electric motor. It's an engagement with a larger gear, okay, which does two things. Number one, it's going to slow the speed down, because if this is coming off and it's rotating at a faster speed, it's going to go around more times than the larger one that's an engagement with this this gear. Okay, so it's going to slow the speed down. It's also going to increase torque, which we're not going to talk about yet. We'll do that when we're in machine elements. But then you'll notice that it's also an engagement with another one that is of the same size. Okay, now in this case, this is it looks like for a scanner or a printer of some sort, and it's going to be pulling a document through the rollers. Okay, so the rollers are actually going to be what's in contact with the paper, but notice that the gears are what's setting up, if you would, the speed coming off of that motor. Now, why wouldn't we just directly, with the same size gear, use it up over here instead of slowing that rotational speed down? Why wouldn't we do that? Say it again. Yes, so gears naturally, this is a great application for this. Gears naturally, when they are enmeshed with one another, are going to change their rotational direction in relationship to another. So Mitchell has a great point. This one is going to go in one direction, this one's going to go in the other. So for it to feed through, we have to have rollers that are going in opposite directions. So yes, gears are like a natural choice for this to get that direction the way we need it to be to operate the scanner. Another reason why we wouldn't just have the motor direct drive, if you would. It's probably going too fast. This is where I usually talk about another place where we might see an application similar to this, not exactly with pulling, for instance, a document or paper through rollers, but think about the conveyor at the grocery store. Okay, underneath the conveyor itself is where the motor and stuff is. If we would have a motor, for instance, that would be direct drive to the belt on the conveyor at our grocery store, what would happen when we set our stuff down? Two things. Well, you're going to have a motor that's going to be going pretty fast, right? So if we set down, for instance, something quite light, okay, it's just going to like take off, right? And it's going to like probably fly past the checkout person to get it itemized. But the other problem is, as Mitchell had said, a lot of times when we have high speeds like this, there's low torque. Okay, and again, we're not so worried so much about forces, but it is something to consider as we're doing our kinematics here. If we would set a case of water on there, even if it's going to be going fast, a lot of times we'll be able to stall it out really easily because there isn't much torque coming off that motor. So by increasing that distance, we get a like a leverage out of the gears, which helps with doing more work and being able to push things along that are of you know, a heavier nature. So so there are a lot of places where we are going to be looking at the application of gears, and they're a very common machine element, and that's why we're spending time here on it. Okay, so let me go back to our PowerPoint. Now, there are a lot of different types of gears. Okay, so as we look at the next page, on page 261, there are a number of different kinds. And like I said, here we're going to be focusing on spur gears because they are the most popular general industrial application. And we get a lot of mileage out of, especially the relationships that are developed here. It just becomes a little bit different, you know, equations on the specific types that you would get from like a manufacturer, for instance. So let's take a peek at all the different types of gears that we have shown in figure 10.3. So as we're at the top here, this is going to be our classic spur gear application. So so you'll notice that the teeth here are just, you know, straight across the face, meaning they're parallel to the center of the shaft. The two shafts that are going to be of interest here, one for what we call the pinion, which is going to be the gear in mesh that is smaller and has fewer teeth. And then we have the gear itself is going to be the larger gear that's enmeshed with more teeth. So, so the shaft on the pinion and the shaft on the gear are parallel. Okay, that's the arrangement that we have with spur gears. We'll be looking at the actual tooth formation in a bit, okay, but it is the most popular, and it's the one that we see in a lot of different applications. Now, as we go over to the right, we actually use the very same tooth arrangement that we see here on a rack and pinion. And a rack and pinion, the only difference here is instead of taking rotational speed and transmitting it to be another rotational speed, what we have here is we have rotational speed that's going to be turning into linear speed. Okay, that's the only difference between the two. And it's kind of like taking, if you would, the outside face of the gear and like laying it out flat. Okay, but still the same teeth engagement and formation. We also can have what we call internal gears. So here you'll notice that we have our pinion running on the inside of, so just another arrangement. And then the next one that we have is going to be helical. Helical gears are similar to spur gears, except you'll notice that the teeth are going diagonal across the face rather than being parallel, okay, or a straight line. Now, this is advantageous for two reasons. Number one, this means that we can take a side load, okay, that we have some resistance to force that is coming along the axis of the shaft. In the case of spur gears, we can only have forces that are perpendicular, okay? A little bit of side load it can take, but really not designed for that. Helical gears can take that, okay? That's meaning that we have something coming in on the side. You guys have had statics before. This is where you have that X component at the you know, at the reaction, for instance, of a beam, which can also be like a shaft, okay? Additionally, they are going to be able to push more torque through them because they have a longer line of engagement, okay? When we just have the line going straight across, all we have is the face width to distribute the load over, if you would, okay, and to push torque through. On a helical gear, on the other hand, we get more distance because of the angle that's created across that face. So we have more line that we're distributing that load over, okay? Additionally, they're a quieter gear. In the case of a spur gear, as one tooth is being unengaged, the next one is coming in, and they have a, you can hear them actually engage, you know, click, 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 click as they go along. Where a helical gear, again, because of the nature of that angle, you have partial engagement from the previous tooth as you engage with the next tooth. So they end up being a quieter gear set as well, okay, which is nice. The next kind that we have here is going to be a herringbone gear. Here you'll notice that we basically have two helicals that are opposing one another. And again, it's going to be, we're spreading the force over longer lines so we can push more torque through, and it's also going to be a quieter, more low profile type of an application. The bevel and the miter gears. Now, these look very similar to one another, except there's one big difference. A miter gear, the two gears are going to be the same size. On a bevel gear, you're going to have one that's going to be a pinion and one's going to be a gear. They're not going to be the same size, but their relationship of 90 degrees to one another as far as one shaft to the next is going to be the same. So 90-degree application here as opposed to having parallel shafting, okay? The other place that we can get parallel or perpendicular relationship from the input, if you would, to the output gear shafts is going to be with a worm gear, okay? A worm gear, you're going to notice, has this spiral. That's the worm, okay? And that's going to drive then the rotational speed of the actual gear itself, okay? So again, this kind of looks like a helical, and it does, but it is going to mate specifically with the worm, okay? So just another type of gear arrangement. So any questions kind of on different versions of gears that we have that you may have seen in application or experienced out in industry?
I had a question about the worm gear. You said the bottom portion of the worm and the other output.
Mm-hmm. Mm-hmm. Yeah. Now, kind of interesting. I was reading through the book again, and I try to, you know, kind of prep myself. I found it interesting because it said, if you turn the page, it says that worm gears are typically not reversible. That's actually not true. Actually, applications that I have specified actually use them specifically on servo motor applications when you do have things that are going back and forth in different applications, because they have what we call zero backlash. And we'll talk about backlash in a little bit. And that's really just kind of a gap between when you change directions. So, so I found it interesting that they specifically said they're not normally changing directions, but actually in many applications, especially servos, you put worm gears on the end because they are a lot more accurate and provide zero backlash. Okay. So, so any other questions or comments? Okay. Anything out in like in automation. We used to use them on packaging equipment, high-speed packaging equipment. We used to use them on robotics that we had. Yeah, anywhere that you need to, for instance, start and stop an application of, you know, like along the length of. So, so when I was at Hyson, we did high-speed wrapping equipment, and we would run servo motors exactly like this with worm gears on the end of them so that we could start and stop like as we indexed, for instance, product into our wrappers. Mhm. What was that? They can go either way. Yeah. Yeah. And maybe it's a specific kind, but yeah, they can definitely go in the reverse direction. See, I see another comment. There we go. Lots of configuration. It has all, oh, thank you, Jason. So you can see the movement. Oh, great. So Jason, in our chat, what I'll do is, that's great. I'll add that to the, like a resources page, and then we'll check that out. Cool. Awesome. Thank you, Jason. Okay. Let's go back to our PowerPoint. So we talked about each one of those. So let's look specifically at spur gears. So what we're going to do is we're going to turn our page, and we are going to look at, starting at the bottom, there's a couple different figures that we're going to be referencing, but starting at the bottom of page 226. So I'm gonna go underneath here, and what we're going to look at is going to be kind of the profile. It's called an involute profile of a spur gear. And we're going to kind of see a couple teeth here to give us some kind of baseline terminology. So first and foremost, each one of these is called a tooth, okay? And you probably have picked that up along the way. You'll notice that there is this line in the middle right here. This is called the pitch circle. Okay, or the pitch diameter, if we're looking at the distance from, one side of that circle to the other. So pitch circle and pitch diameter refer to that right there. Now, it looks like it's about halfway up the tooth or halfway down the tooth, but it's not exactly there. The distance from the top of the tooth to that pitch circle is going to be called the addendum of the tooth. And the distance from that pitch circle to the bottom or the root of the tooth is going to be called the dedendum. The dedendum is always longer or larger value than the addendum. And the reason for that we'll be seeing is so that we don't have any what we call interference of the teeth as it comes down in here. Okay. Another characteristic of a tooth is going to be its face width. Okay. That's going to be how long or how thick the faces that we're actually going to be, having contact with or transmitting any force through. I'm going to peek back and just kind of see if there's anything else from here. Pitch diameter we talked about. Okay. Addendum, dedendum. All right. Now, what I'm going to do is I'm going to show you two teeth that are in engagement. This is kind of a cool illustration or little. Here, let me see. I'm gonna put a couple pieces of paper down so that hopefully online this is easily seen. Okay. So what we have here is we have a couple teeth that are simulating, a full rotation for gears. So as I move this, if you would, back and forth, okay, we are going to see these teeth in engagement. Now, as I said earlier, when we look at the point, the pitch diameter sometimes is referred to as the effective diameter of the tooth. And if we look, it's along this yellow circle right here, okay? It also happens to be the point that this, for instance, the red tooth is going to have contact with the yellow tooth, okay? Now, as I stated earlier, if we kind of get these up and down, see the yellow between the teeth here. I don't know if I can maybe go like this for you guys. There is this gap in between, okay? There is this gap in between the bottom of one gear to the top of the next gear's tooth. This is clearance, we call it. And that's why the addendum of the tooth has to be shorter than the dedendum, because the addendum is from the top of the tooth to that pitch circle. And then the dedendum is from that pitch circle to the bottom of the tooth. If they would be the same size, what would happen? Well, yeah, okay, but why would they heat up and crash? Well, yeah, but why is it important that that D-dendum is larger than the A-dendum?
Wouldn't they just bind?
What was that?
Wouldn't they
It's gonna be
bind?
quieter. We don't want to have interference, right? We don't want to have metal shavings right off the bat, right? And it also means that we have to mount these correctly on the correct centers, okay? So if this is off by too much, it's gonna push that gear down or too far up, right? And then we could have problems. So when we're looking at mounting gears or determining the center distances and such, we have to be aware that, you know, we've got a clearance that we can work within, but we can't exceed that or have those teeth bottoming out. Okay, so as the designer, you get to have that responsibility. Okay, so just keep that in mind. Now, as we move along, these are like what I said, the involute tooth. So you'll notice that it kind of comes up, and then it's gonna have a radius there, and if you can kind of see, it's gonna always hit that very same point. That again is the pitch circle of one gear, is going to be tangent to the pitch circle of the other gear. So if we draw them in, for instance, a layout, we will always show these pitch diameters tangent to one another. Okay, you may or may not show the actual tooth for each one of the gears, because that takes up some data, and it kind of, you know, can sometimes be you know, a little bit bogging down. But at the very least, to determine where these are going to be going, because they overlap into each other, you have to show the pitch diameter tangent to each other. Okay. All right. Pressure angle. Pressure angle. Let's take a look. We can see that on here as well. So pressure angle is going to be the angle for which the line of action comes in as a, what we call a, it's going to be the resultant of the tangential and the radial forces, okay? And it's going to be along this line of action. Now, we would measure that line of action with a horizontal, and we are going to get three options for pressure angles. The three options, and these are the only ones that are out there, are the 14.5, the 20, and the 25 degree, okay? Now, 14.5 are for replacement parts only. We do not make any new designs with 14.5 pressure angle, ever, okay? 20 and 25 degree pressure angles are the most popular, with 20 being the one that is kind of like most universal, okay? Yes.
So what do you mean by a replacement part? So like say the original part might have been 20, but then when they replace it, it's gonna be 14.
No. It means that in the past, they used to design with all three. And there's going to be existing machinery out there that has 14.5 pressure angle, okay? And the only time we make 14.5s is for that existing equipment that's already out there. Any new designs, we use 25 or 20, okay? Now, pressure angle is important. As you can see, that is going to dictate, you know, how these come around. So if we change the pressure angle, those two gears will not mesh with one another, okay? So there's two things that have to be common between gears. Number one, diametral pitch, we'll see in just a bit, but the other one is pressure angle. So two mating gears have to have the same pressure angle. So again, new designs will always be 20 or 25 degree. With what we're going to be looking at, it's always going to be 20, because that's like general industrial. That's usually where we always start, unless there's a reason not to. Okay. Yes.
So what, can you like go over that again? What exactly?
So as we look at this line of action here, there are going to be two forces. As these two hit each other, okay, as these two hit each other, there's going to be a tangential force and there's going to be a radial force that occur. And the resultant of those two forces is going to be along this line of action, okay? And that angle with the horizontal is going to be the pressure angle. Okay. And like I said, if we have a 20 degree and a 25 degree pressure angle, even if the diametral pitch is the same, they do not mesh together. Okay. They have to have the same pressure angle always. And that's part of what we do when we specify gears. We have to specify the pressure angle as well. Okay. When we call it out. All right. Let's peek back. I just want to see it. I did data. Diametral pitch, okay, diametral pitch. Diametral pitch, we're gonna go back into our book and we're gonna be looking at page 263, okay? Diametral pitch is going to be a number, okay? Sometimes we call it the gear number. What number is that gear? That gear number corresponds to the size of the tooth, okay? So the higher the diametral pitch, the smaller the tooth. The smaller the number, the larger the tooth. So you can kind of see here, this is a, 48 as opposed to a 3. Physically, a 3 is going to be much larger than a 48, okay? Now, the equation to calculate, or that kind of relates a couple things, is going to be diametral pitch, which is going to be capital P sub D, diametral pitch. It's going to be equal to the number of teeth, capital N. Now, number of teeth is literally just counting around the outside of a gear, how many teeth are on it. That's it, okay? So if I have a gear like this, I can count how many teeth there are. That's my N in that equation, okay? And then lowercase d is pitch diameter. Lowercase d is pitch diameter. So, I think it's a couple of pages. Okay, here we go. On page 273, this is just so that we can see two gears that are in mesh with one another. So on the left-hand side, this is on page 273, and this is figure 1012. On the left-hand side, we have a smaller pinion gear. And you'll notice that they have the D, lowercase d, which is pitch diameter. That's its diameter of that effective circle, which is then going to also represent that point of contact that it's going to have with the other teeth on the other side. So when these two come together, those pitch diameters are going to be tangent to one another, okay? Now, pitch diameter is the diameter that's created from the tooth, or from the number of teeth at the size that we're calling them out as. So diametral pitch is size of tooth, number of teeth N, okay? And then pitch diameter. So the more teeth that we have on the outside, the larger that diameter is going to be. The fewer teeth that we have around the outside, like the pinion here, the smaller that gear is going to be. All right. So if we want to figure out, if we know, for instance, the number of teeth, and I know the diametral pitch of a gear, I can always figure out what its pitch diameter is going to be. So this is going to be one of the first equations that you want to add, for instance, if you're keeping track of equations from this chapter, okay? So capital P sub D is equal to N divided by lowercase d, where capital P sub D is equal to diametral pitch, okay? Diametral pitch. N is equal to the number of teeth. And that's going to be on whatever gear we're dealing with. Okay. And then lowercase d is going to be pitch diameter. Okay. Now, just as we're looking at these three terms, there's two that sound very similar, but they are very different. Okay. Diametral pitch is always size of the tooth. Okay. And it's a integer, it's always an integer number, always. Okay. And it's not every number. So if we go back to page 263, 3, 4, 5, 6, then we skip 7, there's an 8. There's a diametral pitch of 10, 12, 16. Notice it's not all the numbers in between. Okay. So diametral pitches are going to correspond to actual tooth sizes. Okay. Size of the tooth, diametral pitch, capital P sub D. All right. And then when we look at pitch diameter, that's the physical size of the effective diameter that is going to be the two circles that are going to be in mesh. Okay. So if I would take half the pitch diameter for each of these, I would have the center distance, for instance, right? Okay. So pitch diameter, lowercase d, diametral pitch, uppercase P. Sounds so similar. And that's why at the beginning here, it's a little confusing, or it's just keeping them straight, honestly. Now, when I look here at the units, it's important to do this because whenever we see diametral pitch, it'll never give us units. It's just going to give us a number, but there are units associated with diametral pitch, okay? And the units are going to be teeth per inch, okay? So diametral pitch units are teeth per inch, but we'll never see them like that. It'll just say number 10 gear, that's it. A diametral pitch for a gear is 12. But they're not going to tell you it's teeth per inch, but that's what it is, okay? You're also going to notice in the examples in the book, they're not going to show the units so that they cancel, but we're going to be doing it for the work that we do, okay? And I'll show you that as we do some examples here, okay? So number of teeth are going to be exactly that. Teeth are going to be the units, and then the inches are going to be the units for pitch diameter. And then diametral pitch are units of teeth per inch. Sorry, I'm kind of running out of room. Okay. This is a fundamental relationship that we have with all gears, whether they're spur gears, helical gears, anything like this. Okay, this is all going to work out all the time. Okay. All right. So let's take a peek at the bottom of page 263. Okay. So down here, you're going to notice that we have standard diametral pitches, and they have coarse pitch and they have fine pitch. Coarse pitch and fine pitch. Again, notice that we don't have numbers for every single integer number. All right. Coarse just means these are the bigger, chunkier teeth. All right. The lower the number, the bigger the tooth. The higher the number, the fine pitch, are going to be the smaller the tooth. Okay, now I'm going to be sending these around the room. Kind of here. I've got a couple of sets of gears here. Now I've got this set and I've got that set. Okay, now when these go together and they actually fit, they have the same diametral pitch and they have the same pressure angle. They don't have to have the same number of teeth, but they have to have the same diametral pitch and they have to have the same pressure angle for them to nicely move along, okay? And you'll feel this difference, okay, when I pass them around here. Same thing with this one. These two go together really nicely. That means that they have the same diametral pitch, same pressure angle, okay? Always. Now, if I try to now these look pretty darn close. If I take these apart and I try to put them together, you will feel the difference right away. Okay, and it won't take long. They'll start to wear into each other, if you would. You'll start losing material between the two because they'll be shaving each other off. And then all of a sudden, you are going to find that your gears are no longer going to, work the way they're supposed to, and they'll prematurely wear. Okay. So I'm going to send these around the room here so that you can kind of feel that difference between the two. And I'm also going to send my little thing here that you can kind of push around. Unfortunately, for those who are online, you don't get that benefit, but that's okay. Hopefully it kind of gets the point across. So you know what, I'll start this over here. All right. Okay. All right. Okay, so that's kind of our first look at some relationships here. Any questions so far? Not a hard equation at all. The biggest challenge is just going to be keeping track of when you're worried about diametral pitch and when you're worried about pitch diameter. That's usually the first challenge, and lining those up in a problem. Okay. All right. Involute tooth profiles. So again, that is going to be the profile that we see that is created by the teeth that are coming together. So at the bottom of page 164, these are nice kind of a diagram, and also at the bottom of page 150 or 165. So let me go underneath here. So an involute tooth on a spur gear is always going to look very similar to any one of these three. This is a diagram that is specifically looking at the different pressure angles. Okay, and we've already talked about that in the line of action that it makes with. And then over here on the left-hand side, you're going to notice that they kind of show you how to construct an involute tooth. Okay. You will not be constructing these, okay? In modern CAD systems, you just plug in the variables and you're off to the races. You don't even have to worry about it. In the olden days, we used to have to simplify how we actually showed them, where we might show a couple teeth that were in engagement, and then the rest of it would just be the pitch diameters that were tangent to one another, to save, if you would, data or space on a hard drive or on a network. That's not the case anymore because it's just different now. So CAD systems will like automatically generate these paths for you, and all you have to do is put some of the variables in. So. Let's look at example 1 and do this together and kind of go through the process to get us familiar with, a couple, this relationship that we have between diametral pitch, number of teeth, and pitch diameter. So on the top of page 266, we're going to be looking at problem 10.1. Now, I did cross out a couple of the items here. It says we have a 20-degree full depth involute spur gear with 35 teeth. It has a diametral pitch of 10. Determine the diameter of the pitch circle, which is the pitch diameter. Okay. Okay, thank you. The pitch diameter. And then it wants you to do the circular pitch and also the base circle. Now, as I said earlier, it used to be that you would have to kind of calculate these, construct these, draw these out manually if you would, whether it was, on, a board or with pencils and paper, or even if it was in a CAD system that was just 2D. But now we have the means to put this in. So really the only thing that we are most interested in is going to be the pitch diameter, which then will equate to, it'll help us determine what center distances are. So we're just going to look at the first part here, where we're going to calculate the pitch diameter. So as we look at this problem, what you always want to do, okay, and I have these questions kind of listed here. Well, I don't. I'm sorry. We're gonna add them. We want to determine what the pitch diameter is of the gear that they describe here. So first and foremost, we have a 20-degree full depth involute spur gear tooth that has 35 teeth and a diametral pitch of, okay? So as we look and we want to figure out the pitch diameter here, we want to go back to the equation that we're going to be using for this application. So diametral pitches are going to be our capital P sub D. Pitch diameter is going to be the small d. And then number of teeth is going to be our N. So in this problem, which one are they asking us to solve for? Diametral pitch or pitch diameter? Pitch diameter. So what am I expecting my units to come out to be? Nope, not diametral. It's going to be inches. So remember, pitch diameter is that distance across the effective diameter that would be in tangent with whatever it's in engagement with. So I'm going to just reference back to page 273 here. Pitch diameter is this diameter right here that they're showing as like a center circle. Okay. What is that distance across? That's going to be our lowercase d. Okay. And what they're giving us in the problem is they're saying that they did tell us the diametral pitch is 10. The diametral pitch is 10. So remember, I told you there are units associated with diametral pitch, and those are going to be teeth per inch, teeth per inch. So we are going to rearrange this equation to solve for lowercase d for this problem. So as we look at example 10 here, okay, we know that our P sub D is equal to 10, and I'm going to write the units next to it, teeth per inch. Okay. We also know that the number of teeth is 35. Okay. Now, this is just one gear, but if I were to specify a gear that this is going to mesh with, what does its diametral pitch have to be? Same, it has to be 10. What does its pressure angle have to be? It has to be 20 degrees, right? So diametral pitch and pressure angle have to be the same for two gears that are enmeshed. Number of teeth can be different and many times intentionally different, right? Because we want to change usually that rotational speed. Okay. So then we want to find out what is the D of this, right? The lowercase d. So if our base equation is diametral pitch is equal to n divided by d, we want to rearrange this to solve for our lowercase d here, okay? So that means that we're going to multiply up, right? And then we're going to take this diametral pitch and put it underneath. That's what I say. I always like to say I'm doing opposite. So this would rearrange to be pitch diameter is equal to the number of teeth divided by the diametral pitch. Does that make sense to everybody? Okay. So now we're going to plug and chug. That's what this becomes. So if we know that our number of teeth is 35, we're going to put teeth in back of it. Okay. You have to put your units in. I know the book doesn't do it. And then their units magically appear. Okay. No, I want you to cancel them out and be sure that you're getting the correct units. And then our diametral pitch is going to be 10. And we have to remember that this is teeth per inch. Okay. Teeth per inch. So now, as we look at our units, before we even worry about solving for the number, notice that your teeth cancel top to bottom, but we have per inches in the denominator. Do you remember from algebra that that is actually a multiplication on top in the numerator? It's kind of like dividing by 1/2 is multiplying by 2. Do you remember that? That's exactly what the units are doing here. Do it. Divide 1, say take 1 and divide by 0.5. It's 2. If I write it in that same form, if you guys haven't seen that before, if I take 1 and I divide it by 1/2, okay? So for instance, if I say x is equal to 1 divided by 1/2, the ones cancel here, but I've got 2 in the denominator of the denominator. So it's actually a multiplication on, I say on top by the numerator. It's like taking 1 divided by 1/2. It's actually 2, okay? So that's going to equal 2. So the units do the same thing. I've got inches. I have divided by inches or per inch in the denominator of the denominator. So that means it's a multiplication up. So the units end up being inches here, which is exactly what I'm looking for a pitch diameter, right? So if I take 35 and I divide by 10, I end up with 3.5, and then inches are going to be my units. So I want to see, number one, if you want to rearrange first or last, I don't care. If you just want, I just need to see the equation in variable form first. Okay, make sure you do your algebra correctly, that you have it rearranged correctly, and then plug in your values with units, cancel and or combine as needed, and then show your final answer as you see here. Now, the deal is when you show your final answer, if you're solving for a pitch diameter, your final answer should say D is equal to my number with the units and then a box around it. Don't just send me this and say 3.5 inches with a box around it. Okay, that's nice. But what does that equal to? Answer the question. D is equal to. Okay, the pitch diameter is equal to. All right, you don't have to write out pitch diameter, just use the variable that you're solving for in this equation. Does that make sense to everybody? Okay, cool. Any questions there? These are fun. This is gonna be good. This is as hard as it gets. That's the nice thing about gears. They're actually kind of a fun chapter to work on, because you don't get tripped up too much in the math of things. Okay, but you start seeing these relationships. Okay. All right, let's look at standard gears. So I'm going to look at table 10.3. So so as we look here, this is something I got to do. When I started in mechanical design, we still had the drafting boards, and it was a conversion over to CAD that was just starting out. So when we were drawing, for instance, tooth profiles, we would use these equations to find the addendum, the dedendum, and such. And you'll notice that they're all dependent on what do you see in these two columns. PD, what's PD? Nope, not the pitch diameter, it's the diametral pitch. So all of these relationships depend on the diametral pitch, which is the size of the tooth. Okay, which is the size of the tooth. So if you wanted to, you could go ahead and calculate each one of these values, but notice that these are all the same values for any one size that we would want. So we would end up, if we needed to, we could figure out, okay, for a diametral pitch of 10, what would the addendum be on a single tooth? What would be the dedendum on a single tooth? And so on. And it's all dependent on what number or what family, if you would, or what section we're in for that tooth size. Okay. All right. Let's look at the relationship of gears and mesh. So we're gonna skip ahead to page 268, where we talk about center distance. Okay, this is going to be the next equation that we're going to add to our little equation sheet here, if you're making one up with me. So I have mine started. So center distance is simply going to be that center to center distance between two mating gears. Okay, and I think that's pretty self-explanatory, but we might as well look back at page 273, where we've got that nice picture. So you'll notice here where we have our gear and our pinion and mesh with one another. As we look at the centers of each of those, the distance between those two centers is our center distance, capital C. Okay. Now to calculate that, when we know what the pitch diameters are of each one of our gears, we just divide it in half, right? We take the radius of one, the radius of the other. So if we know the physical, or we calculate what the physical diameter is, and determine then, find the radius of each, we just add the two radiuses together, and there's our center distance. Okay. But depending on the information that we have available, and knowing our relationship of diametral pitch is equal to the number of teeth divided by pitch diameter. Oh my goodness. Problem I have is no matter where I go, there's never enough room for me to spread out to try to get this all underneath. Okay, so on page 268, you're going to notice that we have a couple equations here. We've got equation 10.7 and we have equation 10.8. 10.7 is determining the center distance based on what we had just talked about, whether knowing the pitch diameters or the radiuses. Okay, so you'll notice that the centers of external gears here, so like the regular types of spur gears that we've been looking at, where we have the mesh on the outsides, not internal gears, we're going to take the radius of 1 plus the radius of 2. Number 1 is always going to be our faster rotating gear, the pinion. Okay, and most often it's always going to be the smaller of the two that are in mesh. Okay, number 2, R2, is going to be the radius of the gear, which is going to be the larger of the two in mesh. Okay, and it's going to have more teeth on it, so it's usually going to be a larger diameter, larger radius in this case. So we would add the two radiuses together, or we could simply take the two diameters, add them together, divide by 2, and there would be our center distance as well. Okay, so what if we have the physical dimensions for the pitch diameters? Okay, we can use either one of these. Now, knowing that relationship where a pitch diameter is equal to the number of teeth divided by the diametral pitch, we can rewrite it so we would have this form. So for instance, a lot of times we know the number of teeth and the diametral pitch of a gear. Okay, like just knowing it without necessarily calculating that pitch diameter. So we can plug these in. We can take the number of teeth on each one of those, add them together, divide by 2, but also divide by the diametral pitch. Okay, so these are the two versions of the center distance equation that we can use in order to determine center distances. So I'm going to add those to my equation sheet here. So I'm going to say center distance is equal to R1 plus R2. Okay, where R1 is equal to the radius of, I'm going to say pinion. Okay, because the pinion is always going to be the smaller, higher speed gear in a gear set. R2 is going to be the radius of the gear, okay, which is going to be the larger of the two in mesh. We can also say that's equal to D1 plus D2 divided by 2. All right, D1 is going to be the diameter of the pinion. D2 is going to be the diameter of the gear. Okay, again, pinion is the smaller, gear is the larger. Pinion will have fewer teeth, will be going at a higher speed, and the gear will have more teeth, larger, going at a lower speed. The other equation that we can use is going to be C is equal to N1 plus N2 divided by 2 times the diametral pitch. Okay, so we know that the diametral pitch is the size of the tooth. Okay, so that's up at the top here. And then our N1 is going to be the number of teeth on the pinion. And N2 is going to be the number of teeth on the gear. Okay, so 2's are gears, 1's are pinions. Pinions again are going to be the smaller, fewer teeth, higher speed between the 2 gears that are in mesh. The gear is going to be the larger, more teeth, slower rotational speed of the 2 gears in mesh. Okay. All right. Then let's look. What was that? I can. Do you need a little? Yeah, I'll zoom in a little bit so that you can see it. There we go. So if anybody needs to finish up writing, there you go. Okay. Okay, so the next place we're going to go is, let's do example 10.3. All right. So let's first look at the problem statement. It's on page 268, so just below those equations we were just looking at. So we've got 2. Now, this is where, again, you got to kind of get used to the vocabulary. So it says 2 5 pitch. Now, if I have something that we say 5 pitch, it could either be diametral pitch or it could be pitch diameter, right? But as we look physically at these gears, notice that they're different sizes, right? So that would mean that the 5 is common between the 2. So is that a pitch diameter or is that a diametral pitch? 5 pitch gear. It's a diametral pitch, exactly. It is not a pitch diameter. So this 5 pitch is our P sub D, okay, is our P sub D. Or if we're gonna, you know, kind of start this example, our known variable P sub D is equal to 5. And we know the units of this to be what? Teeth per inch, exactly. So we're going to add teeth per inch right here. So we know our diametral pitch is going to be 5 teeth per inch. Okay, 5. "20-degree full depth gears." Okay, now the 20-degree is not going to, that pressure angle is not going to come into play in any equations that we do. It's not. All right, but it's important to note and to understand that it's something you have to specify when you call out gears. You have to know what the pressure angle is and that they have to be the same between 2 gears that are meshing. Okay, so they'll always add that. They're used on a small construction site concrete mixer. The gears transmit power from a small engine to the mixing drum. So here's our small engine, and then here's the mixing drum. So in between there, here are our 2 gears. Here's our small drive gear or our pinion. And then here would be the larger drive gear or our gear. Okay, pinion, smaller, gear, larger. So the pinion, it says, has 15 teeth and the gear has 30. So this is going to be our N1, right? And this is going to be our N2. I know that overhead is sometimes hard with that. So N1 and N2. So we know the diametral pitch of each one of these gears has to be the same between them. And we know the number of teeth on each. They want us to determine the center distance. Okay, so this is C, right? They want us to determine the center distance. So lucky thing, we just talked about that, right? But let's write down on our paper what we already know. So we know that N1 is equal to 15 teeth. We know that N2 is equal to 30 teeth. Okay. And we want to find out what is our center distance. Okay, what is our center distance? Now, looking back at our equation sheet, we've got a couple equations right here for our center distance. Which one are we going to use? The top one or the bottom one? Yeah, with the information that we have, the bottom one is going to make the most sense because we know the number of teeth in each one of our gears that we have in mesh here, and we know the diametral pitch that each one of those gears is, right? So go ahead, plug in, and I'll compare in just a minute. So set this up the way you would, like if you're handing this in, make sure to write your equation in variable form first, put your units in place, do any cancellations or combining, and we'll compare. So as we plug in our values here with our units, so here's our equation in variable form. Make sure you always start with that. Our number of teeth in our pinion is going to be 15 teeth, plus the number of teeth in our gear is 30 teeth, okay, divided by 2 times the diametral pitch of 5. And this is teeth per inch, right? Diametral pitch, teeth per inch. So now when we combine, now you don't necessarily have to do this step, but I'm going to combine it so that we can see our units underneath here. So we've got 45 teeth on top, right? When we combine those two, divided by 2 times, this is going to be 10 teeth per inch. That doesn't mean we have a diametral pitch of 10, but it's got 2 times 5, which is the diametral pitch. So now units wise, teeth would cancel out, and we've got inches in the denominator of the denominator again. Okay, so that means it's a multiplication on the top by the numerator. So do you see how we have inches for units left over here? It's not radians. Don't think, oh my gosh, we have radians per inch. No, we don't, because these multiply on the top. Okay, so, and it makes sense that inches are left over because this is a center distance, right? Center distance. So if I take 45 divided by 10, my center distance should be, make that a little bit lower, 4.5 inches, right? 4.5 inches. Did you guys get the same number? Okay. And if you check at the top of page 269, that's what they have up there as well. Okay. And they used it the second time here. Now they did it with both equations. Okay. So let's kind of practice using that diametral pitch, pitch diameter, and that number of teeth relationship. And what they did is they went ahead and they actually calculated first the pitch diameter for the pinion, then the pitch diameter for the gear. And then they took those 2 pitch diameters, added them together and divided by 2 and got the same number. So really it was a check to make sure. So let's go ahead and do that because we've got the numbers here. Why not? Okay. So to do that approach, we need our C is equal to D1 plus D2 divided by 2. Okay. So I've got to calculate my D1 and my D2 using our relationship of the diametral pitch is equal to the number of teeth divided by pitch diameter. Okay. What we're going to do is we're going to solve for that pitch diameter this time. So we're going to multiply it on both sides, and then we're going to divide the diametral pitch on both sides. So it's kind of like we flip these two, right? Algebraically. So we're going to have D is equal to the number of teeth divided by the pitch diameter. Okay. So now for our pinion, that means that we would have the number of teeth is going to be 15 teeth, right? Divided by, I'm going to put a 1 in front of this, 1 in front of there, my diametral pitch of 5, and that's going to be teeth per inch. So we get that same cancellation top to bottom. The inches are in the denominator of the denominator, multiplying up. So my D1 is going to be 15 divided by 5, which is going to be 3 inches, right? That's my pitch diameter, the distance all the way across, all the way across. Now I'm going to do that very same thing for the gear. Okay, so I'm going to kind of just put a little line underneath here because I'm going to need that, right? But now I want to do that same thing for D2. It's going to be the number of teeth on the gear divided by the same diametral pitch. So it's going to be, how many teeth was it? 30. 30 teeth divided by 5 teeth per inch. Teeth cancel. We're left with inches in the denominator of the denominator, multiply up. So our D2 is going to be 30 divided by 5. That's going to be 6 inches, right? Okay. Now we have what we need to plug in here, right? So this is going to be D1, which is going to be 3 inches plus 6 inches, and we're going to divide that by 2. So if we take 3 plus 6, 9. 9 divided by 2 is 4.5 inches, right? There it is. So that's what they did. They proved it. They did it both ways to kind of show you that depending on what you see when you first look at the problem, whether it's the diametral pitches and the number of teeth or the pitch diameters, they're both going to come out to be exactly the same. Okay. So questions right now. Oh, no. I don't think so. I don't think so. This is actually, it's kind of the biggest thing with this right now is just keeping track of diametral pitch and pitch diameter. That's really the big deal. And it's not that hard, right? I mean, you just got to kind of just look at what the number looks like, get what they're giving you, and you'll get it. Just, I just want to call caution to that.
All these things are the agnostic, right? So AGMA, they're all AMG stuff. So this is like the equation stuff on the
Oh, right. The American Gear Association or whatever. Yeah, it's like the overseeing body of, absolutely. Yes. Yeah, and that's a good point, Dylan. So when gears are kind of like hardware, right? You don't like randomly, come up with your own socket cap screw, right? You have this like family of things, the same things with gears. Okay. Gear manufacturers are going to all follow these diametral pitches, the sizes of the tooth. If it's a spur gear, Browning, what's another gear manufacturer? Falk, Rush, they're all going to have the same gear across their product lines. They're all going to be exactly the same. So it even comes down to what your standard face width is. So like diametral pitches of 8 are going to have a certain face width, and diametral pitches of 10 are going to have a different face width. And if you're calling yours a diametral pitch of 10, you got to abide by. Well, I'm going to point back to this chart over here. So if we go back down to right here, that chart, they all have to abide by that. Yeah, so AGMA, you're correct. The American Gear Manufacturers Association, I think is what it is. For metric gears, yes. Yeah, they have their own. It's very similar relationship wise, but the numbers are modals as opposed to, like the diametral pitches. Yeah, but there's crossover between the two. So yeah, so that's that.
I was wondering, because when we do gear calculations, we always have to put we use print, like when we make gear software that will print the actual like GAMA spec sheet
Mhm.
attached to all our prints. That's why I was wondering if this is all, you just answered the question. So that's what I was wondering.
Yes, it's all based on that. Now, could you create your own spreadsheet? Sure. If you wanted to. I'm not going to require that you guys do that as part of this class. When you get to machine elements, for instance, the design of machine elements, this isn't so involved right now, right? I mean, yeah, you could do a little Excel calculator if you wanted to, but to me, why not just write it out? It's not that difficult. But when we get to problems, Mitchell had me for, oh, you did too, Dylan. Remember when we did the, did we do gears? We did V-belts.
I think we did gear driven belts, I think.
I forget if it was gears.
Chain sprocket.
Oh,
Chain and sprocket,
that's-
yeah, we did the chain and sprocket, which are similar, but then you start getting processes that are gonna have 30+ steps to them. And then it's nice to have a spreadsheet. Oh, Eric, you were in there too. It's nice to have a spreadsheet to kind of go through that process, that when you get down to the bottom and the stresses are too high, okay, then all of a sudden it's like, oh crap, now I've got to go back through that whole process. And this way on a spreadsheet, you can just massage or tweak a couple of those values, and then you can just like automatically check your numbers at the end again. So in that case, we will be using spreadsheets later on, but that's when we like add a lot of stuff to this, you know, to get to the sizing and the materials and the hardnesses and all that kind of stuff and stresses. So it's something to look forward to, actually. It's fun. But right now it is very simple. Like Dylan said, is this as hard as it gets? Yeah, kind of. It's not that complicated, but there's some important relationships that we want to make sure that we get down here, and vocabulary. So why don't we take a little bit of a break? So I'm going to pause the video right now, and I'll let you guys take a little bit of a break, and then we'll be back and kind of continue on. Okay. All right, so before we kind of jump back into context, I forgot to kind of show you what backlash was all about. We mentioned backlash. They do have a section in here that they talk about backlash. We don't specifically calculate it, but know that it's always going to be a function of any gear set that you have. And the easiest way to kind of, kind of define it, if you would, is to show you. So if I hold my red gear down here and I just kind of rock this back and forth, and hopefully you can maybe hear and or see that yellow one can move back and forth. What was that? Or I can hold the yellow one. Oh yeah, good idea. That you can kind of see this red one go back and forth. And that gap in there is intentional. Okay. Now, some gears like spur gears are going to have more backlash than some other types of gears like the helical, the herringbone, those types of things. And all that means is if I were to reverse the direction here, I would have a little bit of a gap before I would get re-engaged. Okay. Sometimes you can feel this on maybe older types of like knobs and handles that you might have to crank on. And then when you go back the opposite way, you can feel that like difference before it engages. And that's going to be backlash. And backlash will increase as something is used over time, but we need backlash. All right. Why? Why do we need backlash? Like in the case of spur gears, they might not always line up. We need a little bit of clearance. Anything else? What do we do to help with friction, Mitchell? We add what? Oil or lubrication. This is a place for that oil lubrication to get into so that we can then, number one, reduce the amount of heat, the friction. We can pull that away from, as things hit each other. It keeps the noise down, all right, and the wear over time as well, right? So if we keep it nice and lubricated, it's going to last longer, all that kind of stuff. And then this backlash, this space in between gives that lubrication someplace to be as well, okay? Because if we would be like metal on metal, now all of a sudden we've got, it's noisy, it's going to be a lot of heat, stuff like that. Now you can have more accurate grades of gears so that they are intended to run closer together. That's okay, where backlash and these clearances are going to be smaller, but run of the mill, off the shelf, that kind of thing. We're gonna either have to deal with this or go to a different type of a gear that's going to minimize that for your application. Okay. Any questions? So I wanted to show you that before we officially kind of moved on. So let me pull up our PowerPoint, and we're going to skip over to section 10.7 in your book, which is on page 273. And here we're going to talk a little bit more about, well, they call it gear kinematics. And this is where we're going to be looking at two quantities. The first one's going to be velocity ratio. Velocity ratio is defined as the angular speed of the driver gear divided by the angular speed of the driven gear. Now, remember, when we're talking about classic or general applications, your driver is going to be like off the motor. It's going to be the higher speed of the two gears that are in mesh. So it's going to be your larger number, if you would, on top, divided by the lower speed the larger gear that's going to be going slower on the bottom. Okay. And we're going to find out what that ratio is between the two. Okay. There's a couple different things about gears that we can use to get to that ratio, which are going to be found in equations 1017 and 1019. I'm going to peek over to 1019 right away because this one gives our complete list. So on page 274, there is this equation right here for velocity ratio. Velocity ratio is going to have a variable of capital V, capital R. Okay, velocity ratio is going to be equal to. There are 4 different things that we can use to get our velocity ratio. The first of which is going to compare W's. Remember, W is angular velocity, how fast or slow either one of those components is moving. So when we look at number 1, remember number 1 is always going to refer to the pinion. Number 2 is always going to refer to the gear. The pinion is always going to be the smaller, faster rotating of the two that are in mesh. So W1 on top means that we are going to have our larger value on top. And then the smaller value, W2, is going to be on the bottom. Okay. So always think larger number top, smaller number bottom is the classical type of application. Okay. Now we also can compare the physical sizes of either the radius or the diameter. But notice now our 2's go on top because those are the larger of the 2 numbers. So if we look at the radius or the diameter of the gear compared to the radius or diameter of the pinion, we can divide those 2 numbers and we're going to get the same ratio. Okay. And then we can also count the number of teeth, and we can take the number of teeth on the gear, number 2, divided by the number of teeth on the pinion, number 1. Okay. Larger, smaller. Okay. Now, what does this do for us? So for instance, actually, before I look at numbers, let's write this on our equation sheet, because this is another one that we want to add and kind of want to keep in our arsenal, if you would. So VR is equal to, and the 4 versions that we have are W1 divided by W2 equal to R2 divided by R1, D2 divided by D1, and then N2 divided by N1. Okay. Now the only ones that we need to identify here are W1 is equal to the rotational speed of the pinion. Okay. W2 is going to be the rotational ROT speed of the gear. Okay. And then our R's and D's and N's are identified above. Okay. So depending on the information we're given or what we know about the 2 gears that are in mesh, and we only calculate velocity ratio when we are comparing these 2 that are going to be working together. Okay. And once we know, we can pick any one of these and it's going to work out. Yes. 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 So we always want our larger number on top. So when we have a W1, the pinion is always going to be like, for instance, off the motor. It's going to be the faster moving rotational speed than the gear. So this one's going to be the lower speed. But then physical size wise and number of teeth, now the gear is the larger. Always bigger divided by smaller in the application where you're reducing the speed. If you're going in the opposite direction, then it would be opposite. Okay. So any questions here so far? All right, we'll be using this in a couple applications, so don't worry. Now, the other equation that we want to call to mind is the one at the top of page 274. And that looks familiar to us, doesn't it? V is equal to W times R is what we were using previous for our velocities, our straight line velocities, okay? So straight line velocity component, we call this the tangential speed, okay? We're going back over here, and we've been looking at this diagram but for other reasons, but this is really the intention, is to show us this straight line velocity component of the rotational motion of these 2 gears that are in mesh, okay? So VT, so if we look at this in terms of, here is our center of rotation, okay? Here is our radius to the point of contact, okay? And if this is rotating around on a link, notice that this VT, the straight line velocity, is tangent to that pitch diameter circle, okay? So does that all look kind of familiar to us when we look in terms of center of rotation frame, the radius representing a link, and then now as we rotate around, we are going to have this straight line velocity component due to the rotational nature of that link or that gear, okay? Now, the pitch line velocity will be the same for the pinion and the gear, because they're, even though one is rotating faster than the other, the radius is smaller on your pinion and it's going to be larger on your gear. They're engaged with one another. They have to be going at that same pitch line speed. You guys see that? And the difference here is they will rotate at different RPMs, but their radiuses are larger and smaller to accommodate. So whether I determine the pitch line speed on my pinion or my pitch line speed on my gear, or if I do them both, they are going to be the same. They are going to be the same. And notice the rules for direction are exactly what we used before in our previous module, where if I'm rotating in this case, a counterclockwise direction, my pitch line speed, my straight line velocity component is going to be in the direction of rotation perpendicular to its, back to its center of rotation or its radius of rotation, okay? So pitch line speed. So to calculate that, we want to add this because you will be asked to do that a couple times in some examples that you're going to be, or some problems that you're going to be doing for me. Pitch line speed, or tangential velocity, it's referred to a lot of times as well, is going to be equal to the rotational speed of the link times the radius of that link, okay? So VT is pitch line speed. Okay. Now, units. What do we know? You guys know the units of this. What am I expecting for the units of pitch line speed, straight line velocity? It's not that long ago. It was just last week. What was that? Lucky Charms. It is kind of Lucky Charms. Yes, those aren't the units, but okay, I'll refresh your memory. Okay, so I'm gonna put my W here and I'm gonna put my R here. All right. So in here, I need radians per second for my W, right? Multiplied by inches. Okay. So when those multiply out, what do those equal? Inches per second, right? The radians magically disappear. They magically disappear. So when I'm using this equation, my rotational speed or my angular velocity, well, I should put it the same. Let me do it the same. Rotational speed, okay, in and out of this equation has to be in radians per second, right? Radians per second. And then my radius is going to be a distance, which is going to be in inches. And then my pitch line speed is going to be in inches per second, feet per minute. Really, that kind of depends on the industry that you're in. A lot of times with conveyors, we look at feet per minute is a common one. But then for other things like pitch line speed of a gear, we're looking at inches per second a lot of times. Okay. Now, when I look up here, our W does not have to be in radians per second. It can be in RPMs because we're calculating a ratio. So notice that no matter which one I do here, inches would cancel, teeth would cancel, RPMs would cancel. So this is truly just looking at, but just make sure that whatever you pick, it's RPMs and RPMs or radians per second and radians per second for both, because the units need to cancel because ratios are unitless. Okay, ratios are unitless. So any questions so far? Pitch line speed. VT. And it's really considered a tangential velocity because it's tangent to It's tangent to the radius of that pitch diameter. Yep, that's why the T. I'm sorry, Mitchell, would you have a question? Straight line velocity. Straight line velocity and pitch line speed, very same thing. Straight line velocity equals pitch line speed. Okay. Velocity ratio, let's kind of back up and look at that. So now that we kind of have the equations here and we see their relationships, velocity ratio, let's peek back at page 273 and look at these two gears in mesh. So our pinion is going to be the one that is smaller, has less teeth on it. Our gear is going to be the larger one with more teeth. And as the pinion rotates, okay, it is going to be then pushing tooth by tooth the gear to rotate in the opposite direction. So the nature of when these two are in mesh with one another, they're going to rotate in opposite directions. Okay. Now that might be desirable and it may not be. So we'll talk about ways that we can change that. But two gears in mesh with one another, if one's going clockwise, the other one's going to go counterclockwise. Okay. All right. Now, when we look at the velocity ratio, imagine that we're just going to use these numbers for instance. Okay. For instance, to keep it easy, let's say there are 20 teeth on my pinion. Okay. Sorry, you guys online, 20 teeth. Okay. And then let's say over here, I've got 60 teeth. Okay. 60 teeth. Right. On my gear. All right. So for instance, my N1 in this case would be 20 and my N2 would be 60. Right. Now, what can you say about those two gears in terms of how many times the pinion would have to rotate in order to get the gear to just go around once? Eric's holding up 3 fingers. 3 fingers. Mitchell's got 3 fingers. 3 fingers, 3 fingers, 3 fingers. Everybody's got 3 fingers. Good, 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 good. So, what are we noticing here? 60 divided by 20 is 3. N2 divided by N1 is 3, right? And if we would write that out, N2 divided by N1, it would be 60 teeth divided by 20 teeth. Teeth would cancel top to bottom, unitless, okay? And that's the relationship. Velocity ratio is always going to be, how many times does that pinion have to go around? Sometimes referred to as the driver, because that's where like it's coming off the motor, for instance, and it's coming in. How many times does that driver, how many times does that pinion have to rotate in order to get that gear to go around once? Now, that number doesn't always need to be an even number. It can be 2.84 to 1, meaning that my gear would go around once when my pinion would go around 2.84 times. That's okay. It doesn't have to be an even number. Your velocity ratio does not have to be an even number. The number of teeth has to be an integer number. Why? You said it, yeah. And I know, Mitchell, you were getting there. You can't have a half a tooth or a 0.2 of a tooth. You have to have an integer number, meaning a whole number of teeth, right? Whole number of teeth. Okay. All right. So good. Love this. Let's go. Yeah.
Question. There's not teeth values that wouldn't work with each other, right? As long as you have a whole number of teeth or stuff like that.
The only thing, and that's where we're going to be going very next, Dylan. I am going to, as long as you ask that. So Dylan asked, starting on the bottom of page 276, there is a table. He asked about like teeth. As long as you have a whole number of teeth, it's going to work with the other gear. You're correct to a point. So you are going to notice that, for instance, this is the number of teeth commercially available on stock gears. And each one of these sections is a different size of a tooth. It has a different diametral pitch. So for instance, it starts with 32, goes to 24, 20. And as we go to the next page up here, now we start seeing, you know, diametral pitches of 16, 12, 10. Here's where we kind of hang around in industrial applications, right about there. Okay, in the 10, 12, 8s, 6s. Okay, now when we look here, you're going to notice if we look at the diametral pitch of 10, the number of teeth go from 12 to 14 to 15. So we're not using every number. So if I'm like, I want 11 teeth on my gear, you've got to look. Unless you're a gear manufacturer and you're going to make it, you're going to want to buy something off the shelf, right? And so you're going to have to check with that manufacturer and see what's available. Now, if there is a manufacturer making diametral pitch 10 gears, they're gonna do these sizes that are here, but they may add some in between to make their product line a little bit more, you know, desirable. But when we're specifying for our examples here, we're going to use these charts. So it has to be an integer number that's available for that diametral pitch, that size of tooth. Okay, and they're not going to make each and every one. So you'll even notice that there's differences when we're up at diametral pitch of 12. It goes from 12 to 13 to 14, 15, 16, but then it skips 17.
Now, does that only factor in replaceable gears? Like say you have like a seal product where you can't replace the gears?
No, well, it depends on how you are planning to put those gears in there. So if you are a gear manufacturer, so for instance, the place that you work, do they make gears? Some places do.
We just make our own and we do.
You make your own. So that would be a case where you wouldn't have to operate off of this standard. You could create your own gears then, but a lot of places don't make their own gears. A lot of places don't. They're usually going to pull them in from somebody else. Yep, you're going to go to Browning or to Falk or to Rush Gears, you know, something like that. And you're going to then incorporate their gears into, and then they're abiding by this standard. But again, maybe some extras in between, but you would want to see what's available and you can't plan on every number being available.
The software we use is incorporated with EGMA and the ISO standard. So I'm assuming if it's going to spit something out, it would reference.
I would think so. Yeah. And probably like first choices would be using these, but then maybe you guys need to make it a more compact design. So then you might have to massage it from there or tweak it, right? Yeah. Mm-hmm. Okay, good question. All right, so let's go back over here. So velocity ratio, pitch line speed. Let's look at example 10.8. And the example 10.8 is found on page 274. Okay, so it looks like we need to determine the speed of the mating gears in RPM and calculate the pitch line speed. Okay, so let's take a peek at this example. Here we have a set of gears are used to reduce the speed of an electric motor to a shaft driving a grocery checkout conveyor, as we see down here below. So the drive that we're interested in is right here. So coming off the electric motor, we have a small gear, a pinion, okay, in engagement with a larger gear, the gear of the set. Okay, so pinion and gear. And it looks like the number of teeth for each one respectively is going to be 15 for the pinion, 45 for the gear. Probably see it a little bit better in your book. The rotational speed of the motor is 1800 RPMs. And they are telling us that this is a 10 pitch. So that's your diametral pitch. So the 10 pitch here is the PD, not the pitch diameter. So this is P sub D. The number of teeth is going to be on the pinion. That's going to be our N1, 15 teeth. Drives at 1800 RPM. That's our W1. Determine the speed of the mating gear. So how fast is the 45 tooth gear going around? How fast is that 45 tooth going around? And it also says, also calculate that pitch line velocity. That's going to be our VT. So this is going to be VT. Okay. So pitch line velocity. And then we want to know what is the speed of the mating gear. That's going to be our W2. What is W2? Okay. Well, this doesn't look too hard, right? So kind of looking at our problem, what I always like to do, and you can choose, you know, to follow this method or not, but I think it kind of gets everything together for us. You could look at the example and just kind of like go through, but sometimes you're like, why did they start there? Okay. So this is why having the equation sheet is nice, because now you've got everything in one place. Okay, you've got all the variables that you have, the units that you're expecting. And what I like to do is I like to start with, all right, what do I know? And what am I trying to get at? So for example 10.8, we know, what do we know? We know that our diametral pitch, P sub D, is going to be equal to 10, right? And we know that to be in teeth per inch. And they're never going to give it to you that way. You're going to hear it as a 10 pitch gear, number 10 gear. They're never going to say 10 teeth per inch size gear. The diametral pitch is, they might not say that all the time. Okay, so you got to kind of pull that out. We also know that the number of teeth on our pinion is 15. Okay. We know that the number of teeth on our gear, 45. Okay, before we go any further, whoopsie, sorry, falling off here. Before we go any further, as you look at these two numbers, what do you presume or anticipate our velocity ratio to be? How many times does that pinion have to go around to get the gear to go around once? Number 3 again, right? Number 3 is coming up. Now, that doesn't mean that most often it's 3. It doesn't have to be 3. But yeah, if we take 15 times 3, 15 times that pinion has to go around to get this one to go around once. So when we calculate our velocity ratio, it should come out to be 3. Okay, whatever numbers we end up using. All right. Okay, good. And then we also know that W1, which is the rotational speed or the angular velocity of our pinion, okay, is 1800 RPMs. Okay. So this is all of our knowns, right? All of our knowns. And what we're trying to find, okay, what we want to find is we want to know what the speed of the gear is, okay? It's the rotational speed. We want to know what W2 is. And we want to also know what the pitch line speed that is generated between those two gears because they're rotating and in contact with one another. What is that value, okay? So what's the best place to start then? What do we want to do? If I want to find, go ahead. Well, what we want to do is we want to find, okay, what is our W here? And what do we know? If we know W2, right, that's going to be on our gear side of things. We know the number of teeth, right? And we know the diametral pitch, okay? We also know how fast that rotational speed is, right? And we know what the number of teeth are of both. So as we look here, do we have W's? We do. We've got W's here. We've got a W here. We've got some number of teeth here. So what would be the first thing we would need to do in order to find W2? So through the velocity ratio equation here, right, we could set this one, W1 divided by W2, equal to the N2 divided by N1. Is that what you're saying? Yeah. Okay. So let's go ahead and do that. So step number 1 to find, so we're going to try to find our W2. So step number 1, we're going to say, all right, W1 divided by W2 is equal to N2 divided by N1. Okay. And that's from that velocity ratio equation. Okay. This is a relationship. So now what do we know? We know W2, we know N2, N1, and we know W1. So W2 is what we need to find. So go ahead and do your algebra to rearrange this. Now make sure that you know how to rearrange it and that you get your right values on either side of the equation. So I want to get W2, like if you would, on top in a numerator, right? Right now it's in the denominator on the left-hand side. So to get it in a numerator, I need to multiply both sides by W2, right? So that means W2 is going to go up here. So from here, I'm going to cancel this out. I'm going to say, oh, W2 is going to go there. So it's now kind of sitting up there, right? I want to get W2 over there by itself. So that means I now need to get rid of N1. I get rid of, lucky I used pencil. I'm going to get rid of number 1 here. I'm going to take N1 and I'm going to multiply it up here, right? Which then means to get rid of N2, I'm going to multiply it down there. Okay. So rewriting this so that we can see what it looks like. I've got N1, W1, so multiplying those two together, divided by N2 is going to be equal to W2. Do you guys see that same thing? Any questions? Did you guys get the same thing for your rearrangement? Don't be afraid to do it in steps like this, okay? You don't have to see it all in your head. And sometimes it's best to do that, especially when there's a couple steps here to get the things in the right spot. All right, now that we have this here, we can put our values in. So looking back up top, N1 is going to be 15 teeth. W1 is going to be 1800 RPMs. We're going to use those values. So we're going to take 15 teeth times 1800 RPMs divided by 45 teeth, right, is equal to W2. Again, remember, when you're writing these out for me, your units are in all phases of the problem. Now we can take our teeth and we can cancel, right? So we're left with RPMs. That's good, right? I want to try to find a W2. So units for W2 are radians per second and RPMs, right? It's just a conversion between the two. So we can leave it right here in RPMs, which is usually the preferred if we're going to be like using it or specifying it or sharing it with somebody. So I'm going to take 15 times 1800 divided by 45. What do you get? Yeah, 600 RPMs is equal to W2. That's the first part of our problem. Now they may have added clockwise, counterclockwise. So as we look here, they do have W1 going clockwise. So because this is in engagement, which way is our gear going to go? Opposite. It's going to go counterclockwise. So I'll go below it, I guess. Counterclockwise is equal. Let's do that. Counterclockwise. Okay. Now, you're also going to notice, and at this point, when we just have 2 gears in engagement, it's not as important, okay? But it will become important a little bit later. So if you put it on problems like this, where we're just doing velocity ratio, I'm not going to take off if you don't have it. But when we do train values, this is going to make a difference, okay? So I'm going to point out something that they did in this example. You'll notice that they actually calculated their velocity ratio by using the number of teeth and really just kind of did an extra step in here. And they found their velocity ratio to be 3, but they have a negative in front of it. And the negative value just means it is not less than 0. It is not anything else, but it switches direction from whatever the original driver direction was. Okay, that's what the negative does. Okay, we're going to see it's going to come in handy later on when we look at trains. When there's only 2 in engagement, we have like what I'll call 1 velocity ratio because there's only 2 gears in engagement. The positive or the negative doesn't really make a big difference in the final answer because it's really identifying that it's counterclockwise. Okay, that's the negative just means that it's opposite. So if you would stick the negative in there, that's fine. But at this point, it's not that important. It's going to become handy when we do trains. Okay, so that's the first part. Now we need to calculate the straight line velocity, right? Straight line velocity. So straight line velocity, going back to our equation sheet, is our very last one here, right? Straight line velocity. So straight line velocity, we know is going to be the same for both the gears. So when we look at rotational speed here, we do know the rotational speed for both gears now. So we could either look at the pinion side or the gear side, right? 1 or 2. But given the fact that W2 is a calculated value, and we're pretty darn certain on it, right? It's not that I don't think it's right, but it's always good to go with, and a better choice to go with given information, right? So for pitch line speed, we're going to take the W1 or the 1800 RPMs, and we're going to multiply it by the radius back to the center of rotation. Ooh, radius back to the center of rotation. We're only given number of teeth and the diametral pitch. Can I calculate teeth? So I know the diametral pitch and I know the number of teeth and I know how fast that's going, but I don't have the radius, do I? For this equation, I don't have the radius. Can I find it? Yeah, I can. Yeah, I can. If I go all the way back up to the top here, I know the diametral pitch. I know the number of teeth on that pinion. I can calculate its diameter to get its radius, right? Half of that. So that's what we have to do next. Okay, so we get to do next. So I'm going to call this step 1. Step number 2, if you would, or part 2 is going to be our straight line velocity is going to be equal to W1 times R1. Okay. Now over on the side here, we're going to calculate this R. Okay. R1 is going to be equal to D1 divided by 2, right? And we know that the diameter is going to be calculated using this relationship. So algebra wise, the D is going to go up on the top over here, multiply both sides, and the diametral pitch is going to be divided on both sides. So these guys are going to flip, right? They're going to change places. So I'm going to say equal to the number of teeth on the pinion divided by the diametral pitch. That's what's on top for D1. Agreed? You guys see how I did that? Divided by 2 to get the radius. So now putting my numbers in, I know that there is 15 teeth divided by a diametral pitch of 10 teeth per inch. Right, divided by 2. So teeth cancel, I'm left with inches on top, right? So 15 divided by 10 is 1.5. 1.5 divided by 2 is it 0.75? I did it in my head, right? Yeah. All right, that's the number I'm going to put over here. That's the number I'm going to put over here. And then W1, oh, we know that to be 1800 RPMs. Is that what we're going to use there? Go like this. No. We're not going to use RPM. This is back to straight line velocity. In and out of this equation, this needs to be in what? Our favorite. Radians per second, right? Radians per second. So before I can put it in there, my W1 needs to be converted from revolutions per minute to our favorite radians per second. Make sure you show this. I only did it once. Did anybody else get 188.49? Great. Okay, so now this is the number that's going to go up here, right? Okay, so go ahead and do that. So this is going to be 188.49 radians per second times 0.75 inches. Now they put it in feet per minute. don't know if my number's right. .75 times 141.37. And then, so feet, oh, feet per minute. So I'd multiply by 12 and I would divide by 6. Well, I'd have to see, this is why I don't do the conversions. Do you guys get the same thing as I did in inches per second? 141. That's pretty fast, I think. Every second, 1001, 1002. Oops, I got a chat message. What did I do? Yes, that's what I got. Awesome. Thank you, Jason. Okay. So let's make sure now in the book, looks like they are using, their final answer is in feet per minute. Convert our answer here to feet per minute and make sure we get the same number as them. Okay. I'm going to do that on the back side here because I don't have room left. So I've got ET is equal to 140, what's it? 141.37 inches per second. And I'm going to convert that to 12 inches in 1 foot. And I need 60 seconds in 1 minute. So my straight line velocity, oopsie. Yep, 706.85 feet per minute. And that matches what they have in the book. All right, these are fun. I bet you can't wait to do the homework. Like, it's gonna be like, thank you, Kelly, for allowing me that I get to do these. You're welcome. You're welcome. I know, I get it. I get it. All right, we're at 216. Let me see. I'm just gonna peek at this. We did our 8. We're getting towards the end, but you know what? I think this is a good place as a break to just kind of stop here today. The next time we do have, we will pick up exactly where we left off today, and then we'll also add on the rest of the chapter, which is train values. But I want to give you a chance if you're needing to finish up that assignment number 3 or anything else. I want to give you time to work on that. Additionally, get started on this part. So let's look at the homework assignment that you would be ready for, the homework problems that you would be ready for at the end here, that you have what you need. Okay. So on page 295, you're going to notice that the problems start, and let's just take a peek in our module to look at assignment number 4. Okay, I have all the problems listed here. Okay, so we'll kind of take a look at each one of these at the beginning here and see how far we can go, which you'll be able to do some of these. So I'm going to go underneath, and you're going to notice on page 295, number 10.5, okay, is your first problem, and it's just 10.5a, and it says you've got 12 pitch, diametral pitch, 20-degree pressure angle, full depth involute spur gears are used as an on an industrial circular saw for cutting timber. The pinion has 18 teeth and the gear has 42. Find the center distance. Okay, you have everything you need to do that one. Same problem, different numbers for number 10.6, just part A, just the center distance here. You don't need to do the other items here. Notice that on here, it's just 10.5a, 10.6a. All right. Then we're going to go to 9, 13, 14, 15, 16. Okay. Number 9 up here. So 4 problems, 9 through 14. You actually are going to do both of these, A and B, because I'm calling out the whole problem. So you're going to calculate the pitch diameters and the center distance for the description here, where you have 2 mating gears, 10 pitch gears, 18 external. Oh, both external here. I'm so sorry. Both external. Both are external, not internal. So ignore that. If there's any, there are. Shoots. There are internals. I didn't catch that as I was reading this because this is a newer book that I don't have marked up already. So all externals, those are the calculations that we have. You want to find the pitch diameters and the center distances for number 9, 13, and 14 using only external gears. I'll add that note to our module homework or assignment number 4. Okay. The next two, you would also be ready for. Here's the speed of the gear. This is going to be W, okay? And pitch line speed is VT. And you want to do that for the two that you have here. All right. So they're giving you the diametral pitch, the number of teeth on the pinion, clockwise at 18 or 1150 RPM. It mates with a gear that has 64 teeth. Okay. You want to find the W of the gear and the pitch line speed between the two. Same thing for number 16, sorry. So you would be ready for all of those so far. Let's turn the page. Oh, and then here is going to be, yeah, this is sets of gears. That's the very next thing we're going to go over. So you would be able to do, it looks like the first 1, 2, 3, 4, 5, 6, 7 problems in the assignment with numbers 9, 13, and 14, all external gears, no internals. So ignore the internal on the problem statement. You'll notice that you do have a homework answer key here. So if you're working these and you want to peek there to be sure you're on the right track, that's what that's there for. But keep in mind that you're going to be doing written work for this. So I have to be able to read it. So the format that we've been using as we've been going over things, okay, like this is what I would be looking for. Making sure that your equation is in variable form first, putting the units in all phases of the problem, canceling, combining as needed, showing your final answer with its variable called out as well as its units. Okay. Any questions on that? So you could get a chunk of this done. You could do all the way through, it looks like number 16, and then there's only 4 more to go, right? So, we'll continue on from there the next time we're together. Are there any questions before I let you kind of work independently on some of these things and try them out? Okay, if not, then I'm going to stop recording and I'll let you guys work.